So this is my quiz correction for the standard I can calculate force on a charge due to other charges. And I did problem 2174 as recommended, which says two identical spheres with mass m are hung from silk threads at length L as shown in, I drew the figure. Each sphere has the same charge, so Q1 is equal to Q2 is equal to Q. The radius of each sphere is very small compared to the distance between the spheres, so they may be treated as point charges. Show that the angle theta is small, the equilibrium separation d between the spheres is d is equal to q squared L over 2 pi epsilon naught mg to the 1/3. And then it says hint, if theta is small, then tangent theta is approximately sine of theta. So this one reminded me a lot of the derivation for like why pendulums only work when your displacement from equilibrium is very small, like we did last year. So I started off by saying that the sum of the forces in the x and y direction are both zero since it's not moving. And then I drew a force diagram on the right, and only forces I saw were the tension, the force of the electric field from the other point charge, and then mg having it pulled down. So then I broke up the t components into t cosine of theta going up and t sine of theta going to the right. And then from there, I went on and started with force in the x direction. So I said the force of the electric field minus the force of the tension times the sine of theta is equal to 0. And so then I solved force of the electric field is equal to force of tension times sine theta. And then I did the same thing for the y components, where force of tension cosine theta is equal to mg. Force of tension cosine theta is equal to, or force of tension is equal to mg over cosine of theta. And then from there, since I knew we were going to need the electric field, I wanted to keep that in when I did some substitutions. So that's why I solved for force of tension and plugged that back in, yielding force of the electric field is equal to mg times sine of theta over cosine of theta, which was simplified to force of the electric field is equal to mg tangent of theta. And from there, so I wrote down what the force of the electric field is over to the right, and that is the k, constant k times q1 times q2 over r squared. And since it said in the directions q1 is equal to q2, I just simplified that to k times q squared is equal to, or over d squared. There, I saw there was a distance later on. I think I dropped the d and ended up leaving an r. But the distance and radius were equivalents in my proof of that. And then so then I wrote that k times q squared over d squared is equal to mg sine of theta. And that sine of theta came from the approximation the tangent of theta is equal to sine of theta. So like I resubstituted that back in. And what did I do from there? Okay, so I just I said r squared is equal to d squared because I labeled r up in the drawing. And then so I drew a triangle. I guess I didn't draw a triangle, but if you look at the diagram of the ball and you have that as your theta, then sine of theta is equal to the radius over the length because it's opposite over hypotenuse. I did write that over there. So then I substituted that in for sine of theta, and you have mg r over L is equal to k q squared over r squared. Solved for the r cubed, and r cubed is equal to kq squared over, or else L over mg. And then if you take the cubic root of that, you have r is equal to the cubic root of k squared L over 4 pi epsilon naught mg when you substitute in the book's use of k is equal to 1 over 4 pi epsilon naught. That's close to what they had us prove in the book, but rather than having a 4 pi on the bottom, they had a 2 pi on the bottom, and I couldn't figure out why until I realized that that was only the radius from equilibrium to one of the points. You actually have to double the radius. When you put a 2 on top, the 2 cancels with the 4, and you get q squared L over 2 epsilon mg, which is what the book had as well. So yeah, I think that that adequately addresses I can calculate the force of charge onto other charges. And I thought it was, yeah, I'm pretty confident that that's right since I got the same answer that was in the book.